Hello, everybody, and welcome to Tomorrow's Space, Orbit 12.30. My name is Jared. I'm going to be your host for today's show. You probably know me from news. You also probably know that when I first came onto Tomorrow, that I was considered the astronomer of Tomorrow because that's like my thing. And we really don't talk much about astronomy anymore here. But today, we are having an astronomical Ask Me Anything takeover here for you all because we are being joined by Tony Darnell, one part of the deep astronomy group that we have. And Tony, thank you so much for coming on to the show today because there is just so many questions that we have to answer and I don't know half of the answers to any of them. So we're going to see who knows, and if we don't know. So.
Awesome. Well, thanks for having me. And I just got to say, how can you have a show called Tomorrow and not talk about astronomy for a long time? That baffles me.
I don't know. I guess it's just not tangible to folks or something like that.
So you guys, yeah, okay. Just curious.
Yeah, I don't know. I guess you can't like really reach out and like touch it or anything with it there. So it's a little difficult. It's one of those sciences where you really shouldn't touch the science because it could end pretty bad for you.
Yeah, depending on how you touch it. Yeah, that's true.
So we went out and we asked people initially earlier this week, basically, what do you want us to talk about? Because we both are here, so what would you like us both to discuss? And we have quite a few suggestions from our community, and we'll just go ahead and roll into some of those, which one of the sort of overarching ones that a lot of people wanted to know about was the James Webb Space Telescope. Because that's on the horizon. That is like an ultimate machine, and people always love these sort of like ultimate of the ultimates that come out. So with the James Webb Space Telescope, I guess just like a little brief overview about what it is and what it's going to do. Probably to satisfy them at the start.
Okay, so I'll do real briefly. Hold on, I hear an echo.
Well,
all right, I bet.
It's a pretty cool telescope. And it's going to be a space telescope, so good way to do that. All right, and Tony, I'm not going to be able to mime for you there, unfortunately.
Okay, all right.
Yeah.
So there's an echo, so I'm just going to take my earpieces off.
Sure.
So very briefly, the James Webb Space Telescope is meant to be a successor to the Hubble Space Telescope, and it will... it was supposed to launch way back in like 2007 or something like that, and it's been delayed, and there's been all kinds of cost overruns. So now it's been pushed out to about March of 2021. That's when everybody says it's going to be launched. Now the good news is it's finished. The telescope is built and it's all put together, and it's getting ready to be shipped to its launch point, which will be at the French Guiana site, launch site on an Ariane 5 rocket. That'll be again in March of 2021. So it's built, it's ready to go, and the telescope is huge. It's got these, there you go. You got these 19 segmented mirrors that are coated in with a gold coating, and they're coated in gold so that they can be really infrared or reflective in the infrared. And this telescope is much larger than what the Hubble Space Telescope is capable of showing us. And so the big thing here, the big takeaway, is that JWST is going to be able to show us the much more further out into the distant universe. In other words, we're going to be able to see the very first stars ever to shine in the universe. And we're also going to be able to see the very first galaxies ever to form. So that's something that we don't have the capability with right now with Hubble, because its mirror isn't large enough to collect enough light. So JWST is going to do that. It's going to show us the first stars and galaxies to ever shine and give us a glimpse into the early universe, how the universe was created. But in addition to that, it's also going to help us understand a lot more about the nature of planets around other stars, and we call those exoplanets. And these exoplanets are, we now know based on the recent observations from the Kepler Space Telescope, that there are more planets in our galaxy than there are stars. So for every star, there is on average 1.6 planets around it. So there's 60% more planets in our galaxy than stars. And we cannot see them directly right now. No telescope that we have allows us to see them directly with their own reflected light without using some kind of special algorithms and things like that. JWST will let us see them directly. You'll be able to resolve them from the telescope. What's more is that JWST will also allow us to look at the light as it leaves the star, travels through or past the planet. If the planet is between the star and us and the telescope, the light will pass through that atmosphere of an exoplanet if it has one, and we'll be able to tell, first of all, if that exoplanet has an atmosphere, and if it does, what's in it. And that is anybody who's interested in life in the universe knows, that is a crucial thing to know. What kind of chemical elements are in these atmospheres? It'd also be nice to know, sorry about that. It'd also be nice to know it would also be nice to know, I'm really sorry about this. Hold on.
All right, we'll talk a little bit as your dog there seems to be adding in some things with that there. Some really cool things about the James Webb Space Telescope is that because it's an infrared telescope and you're going to be looking at objects with it, you have to be colder than those objects. And Tony, I'm just telling folks about how an infrared telescope works, which is basically you have to be colder than the object you're looking at. So the Webb has to be at minus 223 Celsius or about 50 Kelvin. So super, super, super cold.
That's right. Yes, and I'm sorry about that. Someone just walked into my house and the dog went nuts. So sorry about that. I wasn't expecting that. So yes, that's absolutely right. That in order to see things in the infrared, which is what James Webb will do, we need to be able to get these temperatures of these instruments down very, very cold. And it's got this elaborate, if you've ever seen a picture of JWST, it's got this elaborate sun shield mechanism in it that is designed to keep the sun on the other side of that sun shield and act as a radiator, so that by the time the part, there it is, there's like 5 layers there, and each layer gets progressively colder and reflects more and more heat away from the instrumentation, which is just on the other side. And that stuff is, as Jared said, has to be down to like 30, I think it's 30 degrees Kelvin is how cold it has to get.
It's pretty cold.
And that's, so it's yeah. And that'll be the coldest anything's ever operated in. And also because of the way the size of this telescope, it has to be folded up in kind of an origami, really complicated way that, so it'll fit inside the Ariane 5 rocket. And so that's another big complication to this thing. And one of the reasons it's taking so long is that no one has to build this telescope, as no one's ever done it. And the Northrop Grumman Corporation, that's in charge of, the main contractor that's in charge of it, had a lot of problems dealing with that sun shield. And so finally it's been worked out. They were unfolding it and unfolding it back up again, and they were having trouble doing that. So that was another big reason for the delay on that as well. So it's been a real fiasco in many ways. I was a real JWST fan. I still am, but now it's like, wow, really? Are we still? The thing ended up costing as much as an aircraft carrier costs. It's like $9 billion to build this thing. Now, I still love it, and I still want it to fly. I would spend $9 billion on it. I don't have a problem with it. The problem is it doesn't have good optics, right? I mean, the optics, it has good optics, but this doesn't look good for NASA to be spending so much money on such a project like this. So they've taken a lot of heat and flack for it. Still, though, I would much rather, this is, to me, I don't care what JWST costs. I think it's worth spending the money on. But then, I like this stuff, and a lot of people have trouble with appreciating the amount of money this thing is actually costing. So
yeah, and I sort of like half jokingly refer to it as the telescope that ate the budget, because it kind of did.
You did. Well, the science directorate ended this. They're the ones that are paying for this. The science directorate has, they haven't canceled any other projects because of it, but there's some have been delayed. So yeah, it's definitely the behemoth in the room right now.
Yeah, and the telescope that'll also be coming after it, WFIRST, Wide Field Infrared Survey Telescope,
That's right.
That one is, luckily, that one is so far on schedule and on budget with what they're expecting to have with that there. So pretty good. I guess they've
That's right.
learned their lessons from James Webb and kind of integrated those lessons as well. And
Well, they also got a head start though.
yeah,
WFIRST was one. I don't know if you remember back in 2011-ish or something like that. The National Reconnaissance Office gave NASA two Hubble-like telescopes, two chassis. They were the optical assembly that was identical to Hubble, as well as the spacecraft bus and all that stuff. They had two of those sitting around. Now, why the NRO had two Hubble Space Telescopes lying around, I don't think we want to know the answer to that. But they gave them to NASA. NASA said, "Well, what can we do with these?" And they designed WFIRST to do it. Now that's a good image of the comparison between the two telescopes. You can see the 2.4 meter diameter of the Hubble telescope versus 6.5 meters in diameter of the primary for the JWST. So we're looking at a huge amount of capability here.
yeah.
Also, in that JWST image, off to the right of the JWST heat shield, you see a little thing hanging down. That's a momentum flap, and that's designed to actually not steer, but correct for the solar wind, so that the telescope doesn't get blown around too much, and that helps correct the telescope for the solar wind. So that's kind of cool.
Yeah, and we've
I love
got
that term, momentum flap.
yeah, I like that too. It's like solar, it's sailing. So not only do we sail across the seas, we sail in space as well. And we've already got like a multitude of questions about James Webb, and I feel like one of them is pretty like it loops back to the fact that the National Reconnaissance Office basically told NASA, "Hey, we have two obsolete telescopes. You want these?" And then NASA got them and said, "Whoa, these are good." And then we're all like, "What? Obsolete? Huh?" Sparker on YouTube is asking, if this was used as a spy telescope, what would the resolution of a photo from low Earth orbit be? And I think I can answer this, but I also kind of want to throw it to you too, which is, what do you think?
You mean if you pointed James Webb to Earth, or one of these Hubble?
It seems to be that they're asking about James Webb. I know that the National Reconnaissance Office stipulated to NASA that they could do anything they wanted with the telescopes that they donated, as long as they don't point them back at the Earth. So
Right, yeah.
yeah.
Well, luckily for NASA, the instrumentation that does good astronomy is so sensitive to light that pointing it at Earth would just ruin them. So they wouldn't have that interest anyway.
Yeah.
And other than some climate studies that NASA does with a lot of their weather satellites and geo study satellites that they have, this kind of resolution is not necessary. So you're asking, if JWST were to look at the Earth, what could it see in terms of resolution? Well, theoretically, if you do the math and resolution is always a function of the wavelength you're looking at divided by the diameter of the telescope. Or no, it's multiplied by the diameter of your telescope. So you take whatever wavelength, let's say 700 nanometers is kind of in the red, I believe, and you multiply that by the diameter of the telescope in meters, you'll get some number of let's see, wavelength would be in per meters, and the diameter would be in meters, so they would cancel each other out. You'll just get some number, whatever that is, and that'll you'll get a sense of what it can view. Now, I'm guessing, but I can't imagine that it couldn't, because I'm not doing the math in my head, but it would be something like, if you can't read a license plate with it, I'd be shocked.
Yeah, that would it would definitely be a pretty potent instrument in order to do that. And also for Sparker.
And that's at the L2 point.
Yeah, that's right. Just so everybody is aware, it is being flown to the Lagrangian 2 point, which is the balance between the Earth and the Sun's gravity directly behind the Earth, which is about 1.6 million kilometers away from us. And they're doing that because you can drop it there, and it basically stays there because the Earth and the Sun's gravity balance it out. You have to do a little bit of motion, what we call a halo orbit. You kind of go around that area with that there. But if you put something there, it'll tend to remain relatively stable and stay in just about the same place. Doesn't mean they don't have propulsion on it. They still do. They have the capability to move it. They have reaction wheels, so they're going to use those thrusters to desaturate them, or basically allow the reaction wheels to lose some of their momentum or build up some momentum, and then still be able to use them to control the telescope. And also it's further away from the Earth, so that means you get less infrared interference from the Earth, as well as the moon as well. A lot of people don't think about that. Is that it's not just the sun you have to block this thing from, it's the Earth and the moon at the same time. You want to make it as cold as possible in order for it to work as best as it can.
Yeah.
So.
Right. And I just want to clarify something I just said about angular resolution. So it is, I said it was the product of the wavelength times the diameter. It's actually the quotient of the wavelength over the diameter times the number, just a constant 1.22. So when you divide the diameter into the wavelength, you get a dimensionless number, and that's your angular resolution. So in radians, I think. So you can figure it out. If you just want the diameter of the James Webb Space Telescope is 6.2 meters, divide that by whatever wavelength you're interested in, pick something in the middle of the optical range, although JWST is not that sensitive. It's mostly an infrared telescope, and you can get your answer and multiply that by 1.22. So it's a pretty simple thing to figure out if you want to know what kind of things it can see on a planet. And that's why D, the diameter, is so important. JWST is going to have a big
really big mirror. It's so big.
Really
How
big
is it?
Big,
So,
I don't know. I don't know if it's a program. I was going to say it's got a really big D, but
well, I mean, it does have a big diameter, so
what's that?
I'm just throwing it out there. It is a big diameter, so it's a big boy. So that's how it goes out there.
Sorry.
Yeah. So no,
All
it's
so
okay.
Anyway.
Also, Sparker, just in case you're asking also about like those Hubbles that look at the Earth that the National Reconnaissance Office apparently has, from what I understand, under the best possible conditions with those, you can get like 1/3 of a meter resolution out of them. But that's like the best possible, perfect conditions. If you want to know more, actually,
about 1.5 feet.
Yeah, if you want to know
about a foot, actually.
Yeah, if you want to know more, just a couple weeks ago, someone from the executive branch tweeted images that came from a KH-12, which is the very advanced optical satellites. I won't say who it was.
Oh, was that what it was? Was that the same kind of optical system?
It sure was. So I won't say who tweeted it, but you could probably figure out who it was. We unsure if that was deresed or not, but it was definitely declassified instantly. So there you go. You can also go look for yourself because a lot of us were like, we're never going to see what those. A lot of us were like, we're never going to see what those images would look like, and guess what? Trey Harmon is actually asking a very good question, which is ESA our only option for launching JWST, or did they give us a good deal? And I believe that it has to both contend with we'll fly an instrument if you give us your rocket, and then also the payload fairing size of the Ariane 5 is the largest of the payload fairings of rockets that are flying right now. So you could fit a very tightly folded James Webb inside of it.
Mm-hmm. That's right. And yeah, you're right. So when you design these telescopes, you have two things you've got to answer. What are your science requirements? And then what do you need to build to meet those science requirements? And out of those science requirements, we want to see the first galaxies. We want to see the first stars. We want to see and resolve planets around other stars. All of those were science requirements. And they said, well, what kind of telescope do we have to build to see this? And out pops the James Webb Space Telescope. And then the problem is with these large space telescopes, and they're going to get larger with things like LUVOIR, then how do we get them up into space? And so you have to look at the largest rocket, and you're right, Jared. It was the Ariane 5 was the largest at the time, and so they had to say, okay, it's got to fit in this rocket. So go build it to do that, and that's what they've been working on since forever. And now it's ready to go in an Ariane 5. The problem is the mission has been delayed so much that the Ariane 5 is actually scheduled to be decommissioned in 2020. So they're not going to use. They're going to have the Ariane 6, and you can't just change it. You can't just say, well, now we want to go on a 6. You can't. You're stuck with what you built this for. So the ESA or Ariane Space, I should say. I don't know if they're quite the same thing. is agreeing to keep the Ariane 5 available for this particular launch. So that was a little bit of a scary time when, they delayed it yet again.
Yeah.
It was like, well, guys, we're getting rid of the Ariane 5 here. You need to hurry this up.
Yeah.
And so that happened.
Yeah, so very interesting stuff with James Webb, and of course we're going to watch it because we're getting so close to it. And then just to let everybody know as well, just so that they're aware, from launch, which is supposed to happen, I believe it's scheduled for March 31st, 2021. We'll see what happens with that there.
Right.
I imagine there's definitely a couple weeks of flexibility built into that there, just because of how it goes. But once it launches, it's going to take about a month to get out to L2. And then as it's doing that, it's going to be unfolding on its way out. So for the first 7 days, they're basically going to get all the stuff that they need to communicate and operate and control James Webb with. But then for the 2 weeks after that, like day 8 through 20, that's when all the stuff starts unfolding and coming together and really start going with it. So we're going to obviously hold our breath for the launch, but then we're going to hold our breath for another month as it starts to unfold, and we want to make sure that everything.
It's actually like 6 weeks after launch before you get first light, and it's going to be, all of that's going to be tense. It's going to be tense because think about it. One thing goes wrong. Mm-hmm. It's just, don't even want to think about it.
Yep, I'm not thinking about it.
It's going to be scary.
And also, they're launching James Webb intentionally out of focus as well, because each mirror there has the ability to be dialed in to precisely where it needs to be at, and they're going to do that during the commissioning phase in the first 6 months of the mission there. So actually, as we had earlier this year, on one of our episodes, we talked with someone from the James Webb Space Telescope. They actually said that basically the first images we're going to take are going to be these fuzzy dots of target stars that we already have in plan, and then we're going to move each mirror individually. I think it's something like 1/10,000th the width of a human hair. They can even angle it like something like 1/1,000,000th of a degree, per movement if they need to, for all of these mirrors to finally focus up and get it ready to go. So it's launching already out of focus, just like Hubble, but unlike Hubble, they're accounting for it, and they have a system there that can actually fix it.
Yeah, it's expected this time.
Yes. So
I'm glad you pointed that out.
Yeah. And some other things that we talked about from Isaac X on Twitter was asking about certain planets that have not gotten their own probes in a very long time, which was how about Uranus and Neptune, getting their own probes for further exploration of them? Because we've only studied them very close up with Voyager 2, with Uranus in 1986 and Neptune in 1989. That literally means that since I've existed on this planet, we have not visited either of those. We've looked at them with Hubble, we've looked at them with ground-based observatories, but nothing is as good as actually getting out there and studying them with that. So what does that kind of future look like with those kinds of with those what we call the ice giants, Uranus and Neptune out there? Because I know that they're very much a growing part of the planetary science community that wants to send a mission back to either or even both of those planets.
Yeah, the people I know at NASA are extremely interested in getting back to those planets. The thing about NASA, and we've all noticed this, is that they have to prioritize what they do because of the amount of money that they have. Now, they do incredibly amazing things with what I think is the minuscule budget that they have. And, if they were given even slightly more money. I mean, what is it? I think Neil deGrasse Tyson always likes to say it's like less than a penny per dollar of our taxes go to NASA.
Half a penny, roughly.
And we get all these other things out of it, right?
Mm-hmm.
Well, just maybe 2 pennies, what could we do with that? That would double NASA's budget. And so, it boggles the mind to think about what's possible, but what we're not achieving with our capabilities. And one of those things is Uranus and Neptune. Now, they've had to prioritize in the sense that what they've picked, I think, are amazing missions coming up. The next biggies are going to be the Dragonfly mission to Titan. Absolutely should do that one.
Yes.
That one's going to be awesomely fun. I mean, who the heck doesn't want a nuclear-powered quadcopter sent to Titan? And then there is the Europa Clipper mission to go to the moon of Europa. Now, these are 2 moons in our solar system, which are incredibly interesting because they might harbor life. Or at least we can get a sense of what the conditions might be to have life there. And so those are their high priority things coming up. But people are now starting to talk about Uranus and Neptune. We don't know much about them other than the observations we got from Voyager 2, like you said, as well as the Hubble observations that we get recently. And Neptune in particular is important because it's got a lot of interesting things going on that we have no idea what's happening there. We see these dark spots. We see these light. Yeah, there's a great image of one. I believe, that's a Voyager image, I believe.
Yeah, that's
I'm not
Voyager
sure
2
exactly.
with the great dark spots and the little dark spot below it there during its flyby in 1989.
Yeah, what's going on with that? I mean, that's really cool. Why, these features are something we're just not looking into. So they are starting to, and I think the thing about these missions is that they take not only a long time to get approved, but you got to do the science requirements. Like I said, you got to figure out what kind of spacecraft you want to build, and then you've got to launch it and get it there. Remember, New Horizons, we waited 9 years for that to happen. So we got to do something better about getting us out to these outer planets. And just last week, I did a hangout with some guys at NASA about the nuclear thermal propulsion, which promises to get these space probes out to these planets in much faster times that we're talking maybe 1/3 of the time as it would have taken to get with just using chemical rockets. Imagine 9 years being cut down to 3, right? We can get to Pluto in 3 years. That would be amazing. And it would cut down a lot of this waiting time that we have to get. So we've got a long wait before we see any direct probes getting to Uranus and Neptune, but we're starting now. NASA's starting now to think about it. I think ESA is also doing some work on this. But once that's all built and ready to go and approved, you still got to launch the thing and wait for it to get there. Chemical rockets are really starting to become obsolete with deep space planetary exploration. The next generation of probes are going to have, I think, nuclear thermal propulsion. So look forward to that. That's a huge development in exploring our solar system.
And what's nice is that budgetarily, NASA's getting thrown money to start actually restarting these programs for nuclear thermal rockets. So that was something that was studied very heavily in the late 60s.
It's because it's part of the Lunar Gateway. They want to build tugs for the moon, and it's also it's not part of Artemis exactly, but it is part of the cislunar plan of like using this propulsion for lunar stuff. So that's why.
Yeah, and there's I know that there's some talk about the big decadal survey that's going to be coming up, which for those of you who don't know, about every 10 years, the planetary science and astrophysics and astronomers kind of get together and they basically have a big meeting and they say, what are our priorities we should have for the next 10 years? What are the things that we should really be focusing on? So back in 2010, when that decadal survey came out, James Webb right at the top, and then right below it, Europa Clipper, and then right below it, some sort of Mars sample return mission, which is what they were talking about at that time. And then just below that, WFIRST. So those are so James Webb on its way, Curiosity good to go, WFIRST on its way, and as we found out just about a week ago, the Mars sample return stuff is starting to maybe get some money thrown at it in the upcoming 2020 fiscal year budget for NASA there. So with this upcoming 2020 decadal survey, do you think a Uranus and Neptune mission are a part of that? And also, what do you think are sort of the things that are going to be on that survey?
No, I think the next big things in the decadal survey, I think, are going to be between the Link Space Telescope, which is a new generation of X-ray telescopes, LUVOIR, which is going to be even bigger than the James Webb Space Telescope. It stands for Large Ultraviolet Optical Infrared Space Telescope, and it's going to be a wide-ranging wavelength telescope. And then they've also got there's a couple of exoplanet missions being thought up, and these are people who are already, and I've talked to all of these missions already, who are putting in proposals for this decadal survey to get picked. My money's on LUVOIR to get picked, because that will be the next generation large space telescope that will go up. But that's what I think is coming down the pike. These other ones that would do a Uranus or a Neptune mission, I think would also get done on the same scale as perhaps something like New Horizons. These are different scale missions because LUVOIR would be part of their Great Observatories mission, and New Horizons was part of its Discovery class, I think, mission. So it'd be, I think, something on. These are missions that cost about $500 million to $1 billion, something like that. There are a certain class range of mission. I think those missions would fall under that. They would still get done. And I don't know where they would fall on the decadal survey, but the number one thing that comes out of the decadal survey always gets built.
Mhm.
And as you pointed out in the past, that was JWST. Hubble was also in the top of a list many, many decades ago. And then WFIRST being another one. So these are all things that scientists get together and decide, what do we want the most from NASA? And what are our biggest, I shouldn't say from NASA, in the astronomy community, what do we most want to learn? And then NASA looks at that and says, okay, well, here's what we want. We'll pick one of these. Mm-hmm. And like I said, my money's on LUVOIR, but there's another one that's an exoplanet specific telescope that might work too. That one's looking at directly imaging exoplanets only.
Yes.
That one's another big one.
Yeah. And somebody was actually in our chat room earlier asking about, like, what's the next thing after James Webb, and LUVOIR would be it, which, if I remember
that would be
right,
my money. We don't know it exactly yet.
Yeah.
The thing about it is JWST is going to give us a lot of experience in these origami-like telescopes, right? Mm-hmm. I mean, they want to build telescopes that are 10, 20 times larger than James Webb. And so how are they going to do it? You know, probably after James Webb, this is already maxing our heavy launch ability. You're probably looking at assembling them in space somehow after this. LUVOIR, it would be launched, I believe, if I'm not mistaken, it would be launched in segments and assembled in space. And it would be impressive. It would be really impressive. But we get a lot of experience already from James Webb for the next generation of these. So while I've gotten a lot of flack over James Webb, people get really angry at NASA because it's taken so long. You know, the level of difficulty here is truly astonishing. Stuff had to be invented that did not exist. And that's also part of this decadal survey. It's like when they go to make a proposal, they have to state how much of their project depends on something that doesn't exist yet. And JWST was full of it. It was full of materials that didn't exist, lightweight materials. It didn't hinges and all the boring stuff. All that stuff had to be invented, and beryllium had to be used, and detectors had to be invented that didn't exist before JWST was conceived. And so they build that in. They say, well, this amount of stuff we have to invent. And if it's really high percentage, it probably won't get picked. But something like 20 or 30%, they say, okay, well, we have to invent this kind of technology. We've done this before. We'll do that again. They have a risk management way of figuring that out, not like that flippant way I just said it. But, it is part of the planning process. How much of this stuff doesn't exist? And we've worked out so much of this technology already with JWST. It's going to help a lot with future space telescopes. So I'm excited about that.
Mm-hmm. Yeah, and I can already sort of feel that people in the comments are going to be saying, we'll just stick LUVOIR on a SpaceX Starship and launch it that way. But from my understanding of LUVOIR is that it will be too big, even that, for a Starship to fly it. So on-orbit assembly is one of those things that definitely worth looking into with that there. So there's been some interesting stuff flying around our solar system. In the past couple of years, we've discovered these sort of what I guess most of us are now referring to as interstellar interlopers, which are these objects that we have basically confirmed have come from outside of the solar system and are just passing through, whipping past as they go through. So the first one was back in 2017 with Oumuamua. With that there. And then we just found another one about a month ago it's now called Borisov, after the amateur astronomer who discovered it. So by the way, if you think that all this stuff is just done by universities or all these big names like Keck or Gemini or Canary Islands, Grand Telescope, and all the other stuff, no, they're just Borisov was found by Borisov himself from basically his backyard telescope that he had with that there. So is this sort of like, are we just now discovering these because we finally have the technology to do it? Is that's kind of where we're coming in with it?
Mm-hmm. Yeah, I mean we're seeing these a lot more because we do, yeah, because we're looking for one thing, and second is that we do have the technology. It's gotten better. I mean, stuff that amateurs can buy now is incredible. It rivals anything you can get in a ground-based observatory almost anywhere. Between companies like Planewave and other big instrument makers, you can just really go to town on doing real serious science. And so discovering comets has long been an amateur activity, but this is a new one because these objects are generally quite dim. And the way you know something right now, they don't know for sure that this comet, I forgot the name again, but this latest one is from interstellar space. They're not entirely sure. It will depend a lot on its trajectory, and that's how you know. Most comets within our own solar system, or most asteroids in our solar system, follow an elliptical orbit that's very characteristic of something captured by the sun. So even if it's out of the ecliptic plane, which is where all the planets lie, they lie in this rough plane of around the sun. If a comet comes way from the top and of that plane and then circles around the sun, it still might not be from interstellar space. It could still be from the Oort cloud. It's just coming at it at a regular angle, a strange inclined angle. The way you really know if something is from outside of our solar system is the hook it makes after it goes around the sun. If it's sort of a check mark shape, like a sharp bend around the sun, then that's highly irregular. It's probably not captured by the sun. It's been captured by the sun briefly while it got slingshotted around, but it's not in an orbit around the sun. And that is the indicator that it's from another outside of our solar system, interstellar space. And Oumuamua followed that trajectory, but it was also out. It was on its way out as we caught it. We caught it too late, and so we could only see it as it was passing by. And Avi Loeb, as everybody knows, was saying, maybe this could be an alien beacon of some kind. And everybody jumped on that. But I'll tell you, I appreciate why Avi said this. And I had spoken to him in a hangout many years ago, but I also read his books and stuff like that. He firmly believes, and I agree with him, that it's totally time to start talking about this topic seriously among astronomers. They want the idea of extraterrestrial intelligence and alien life to be seriously considered and talked about within the astronomical community. When somebody like Avi Loeb, who is the chairman of the Center for Astrophysics at Harvard University, starts saying, well, you know what, it could be, he's starting a conversation among his peers that this is okay to talk about. It really is all right to say something about this. Yeah. And so I applaud what he's doing. Oumuamua is probably just a rock, but it's not the point. The point is that he started making this conversation available seriously among the research community. And
and he took a lot of flack for that too. I mean, in putting that out there. Yeah.
But that's what I mean. He's got the scientific standing. This is Avi Loeb we're talking about, saying this. And so he's got a lot of academic capital that he can use on this and bring to bear on it. And I think it's good because scientists are very conservative people. They don't want to rock the boat because they need funding, they need their research grants, whatever it is. And so they're very conservative in what they say in public. And they're also kind of belligerent to each other if somebody starts saying something really out of the norm. And so that's also a big history of science as well, part of it anyway.
And I saw something really interesting about this Borisov coming through, which is that we've caught this one inbound. So we will be able to see it a little bit better than Oumuamua when it came through. And the thing about it is a lot of people are like, well, just build a spacecraft real quick and go intercept it. And that's a lot harder than it sounds. And actually, I just saw that somebody did publish a paper that basically figured out how would we have intercepted Borisov to basically do a flyby of it with something. And they figured out that basically we should have first caught it well in time for us to build a spacecraft to launch it last year in 2018 to get it there. And that spacecraft would basically weigh 10 pounds. So it would basically be like a little bit bigger than a CubeSat. And then you'd have to launch this little 10-pound or roughly 3-kilogram thing on either a Falcon Heavy or an SLS in order to have it actually catch up and intercept Borisov. So This is a lot harder than a lot of people think it is, simply because these objects like Oumuamua and Borisov are moving at tremendous velocities as they come through our solar system, and that's tough.
Yeah, and I just want to add to that this is becoming a real priority for NASA. A lot of people are asking when we're talking about Uranus and Neptune being a cool thing to do, but near Earth objects are starting to become. I think they're woefully understudied by all of us, and NASA has become quite interested in being able to detect these things early, and so they're working also on getting spacecraft in orbit that are dedicated to it. Now, NEOWISE is up there right now looking. It's a wide field infrared telescope designed to look at large areas of the sky at once. But another thing that's going to help us out quite a bit are ground-based sky surveys like LSST. That's coming online next year, and that will take an entire picture of the entire sky, 2 or 3 times every single week. And so we will have these enormous amounts of data coming down from the entire night sky twice, 2 or 3 times a week, where we can then use computers to look at it and see more of these objects. So we're absolutely going to find more. We're going to see more of these interstellar interlopers, as you call them, get through, because we're looking now. We have better techniques to do it.
Yeah.
So that's also going to help.
Yeah, Dr. Hewitt, who works at UCLA, actually came up to Griffith Observatory shortly after Oumuamua was discovered and did a talk about these objects and what to expect. And he says that his hypothesis was basically that within Mars's orbit at any given time, there should be about 25,000 of these objects just zipping through.
That many? Wow, really?
All the way through. So that was the idea at that time. So with Borisov now added in, potentially Borisov added into the mix, I'm sure that number is going to change a bit with that there. But at that time, that's what they were thinking about. So essentially, once we get the ability, like with the Synoptic Survey Telescope, we might start discovering these things left and right as they're coming through.
Yeah.
And also, another cool thing to kind of talk about the LSST there a little bit is that there's so much data coming in from that they actually had to figure out how to contend with that data and analyze all of that data so that you could actually use it. Just because, I mean, it's literally somewhere on the order of, I think one night is something like nearly 100 terabytes worth of data coming from it. It's like some ridiculous number out there with it. So,
Right.
And that kind of stuff you can end up adding on to other things like analyzation of data coming from, say, like James Webb or other things, and that just opens up the realm of possibility for what you can end up studying and how detailed you can end up studying these things.
Yeah, and we're looking at. I met some of the people on the data management team. Shared office with one for a while, and on LSST, and we're talking billions of objects a night have to be sorted through with computers, and obviously no people aren't going to look at it to get a sense of what's new, what transient objects are out there, and things like that. And it's important. And in fact, we were talking about what's it going to take to launch something out to like this particular comet and do it quickly. You're right, you can't do it very quickly. But what'll be interesting about studying this comet is that if we could get something there, these comets have the potential to be responsible for depositing on planets like Earth elements from elsewhere in the galaxy. And so these could be part of the panspermia idea of spreading life across the galaxy. So understanding these comets would be really great if we could get things out there to them.
Yeah,
So,
and just kind of thinking
as
off
a practice, I just want to mention real quickly about Apophis. Apophis is coming up in 29 in about 10 years, and astronomers are planning. It's going to get so close to Earth that it's going to fly underneath geosynchronous satellites, and astronomers are going to use that opportunity to actually, one of the things we're thinking of doing is sending something out to Apophis as practice to see what we can do to get these near Earth objects studied better. So that I thought was pretty interesting, but that's not going to happen for another 10 years.
Yeah, and actually, just a couple years from now, NASA is going to be having a mission called DART, the Double Asteroid Redirect Test, where they're actually going to fly 2 spacecraft to a binary asteroid, where 2 asteroids are actually kind of orbiting each other, and they have an impactor, and they're going to basically fling an impactor into one of the asteroids and see what happens. So, what's it do to the asteroid? How much does it deflect it? What happens to the other asteroid orbiting around it as well? It's going to be pretty interesting to play around with that and see what that goes. Because honestly, one of the biggest threats, other than climate change that we're making ourselves, the biggest natural threat, besides what we make for ourselves, is an impact event from something like a comet or an asteroid coming in. And it's one of those.
I can't believe we're not spending more time on this.
Yeah,
it's really,
and
like hugely important.
You can't like Armageddon it where you've got like 18 days and just launch Bruce Willis and Ben Affleck and hope for the best. Like you need 15 to 20.
He's getting old, We can't depend on Bruce Willis forever.
He
so
is,
we're gonna have to work out another solution.
Yeah, and I don't know if Billy Bob Thornton would really make a good NASA administrator, but I mean, hey, I didn't think Jim Bridenstine was going to be good, so who knows with what's going on there.
Yeah, I mean, I guess he's been a surprise. I was a little skeptical too, but I think, somewhat surprised. There's been some stuff that hasn't been, but yeah. My favorite way, though, my favorite scenario for getting rid of a rotating or an asteroid that's on a direct collision course, and this is a real plan, by the way. If we can detect it far enough away, the plan is if there's a satellite or an asteroid heading towards Earth, we go to it. And we look at its rotation rate, its axis of rotation, and which way is pointing towards the sun. And we paint that side, we paint it white on that side. And the radiation pressure from the sun will reflect off of that white paint and push it just enough, maybe, hopefully, if we get it soon enough, that it will miss Earth entirely. That's my favorite plan. I love that.
Nice.
When I first heard, like, really, you want to go out there and paint it? I'm like, yeah,
might as well.
Banksy on it and stuff. That'd be awesome.
Yeah. So,
but that is an actual strategy.
Yes,
for trying it.
So maybe Sherman Williams can sponsor that mission. So then they can literally cover
a new
world.
Eggshell white.
So yes, that'd be pretty good. My personal favorite for deflection is the gravity tractor. So basically, for those who are watching and don't know, you have an asteroid. You basically fly the heaviest spacecraft you possibly can next to it, and then the gravitational interaction of the spacecraft and the asteroid will cause them to come together. But you don't let that happen. You have the spacecraft fire its thrusters. So that way it just gradually pulls the asteroid out of the way. So it's basically like if somebody gets too close to you and you just like very gently push them very slowly out of the way. That's kind of how the gravity tractor works with that there. And I don't know why, but
it's a good plan.
Just amusing, infinitely amusing to me.
Yeah.
And I want to kind of talk.
Just warp space-time.
Yeah, I was going to say, why don't we talk about warping space-time and some things that warp space-time, like black holes, because everybody loves black holes, because they're so exciting, and we've had a lot happen with black holes this year. Back in April, the Event Horizon Telescope finally wrapped up crunching its numbers and delivered to us the first direct image of a black hole in M87. That M87 is a galaxy in the Virgo cluster. And it has a supermassive black hole, about 3 to 6 billion times the mass of our own. And it made this really interesting image that had sort of like this reddish ring around it. And that was our first time getting a direct image of a black hole. And that was super exciting that we actually got to see that. Like, holy moly.
I know.
Right?
Yeah, that was years in the making. And there were some people that go like, well, I don't get the big deal here. It's just a fuzzy circle. But when you understand how that image was taken and what's behind it, it's actually nothing short of astonishing. I mean, yeah, first of all, black hole, there it is. There's a good image of it. First of all, black holes they've up until very recently been a theoretical construct. They came out of Einstein's relativity. We could do the math, and black holes or singularities were part of that math. And they were an extreme case of Einstein's theories of general relativity. And so everybody's like, well, they should be there. But, no one really saw them directly. We had seen gamma ray jets coming from accretion disks. We'd seen radio bursts coming out of them from other galaxies and other star clusters. And so we figured these must be due to material falling into a black hole. But that's not a direct observation of a black hole. That is the environment around the black hole, and conceivably it could be something else. but that made the most sense. But it wasn't until that image was taken earlier this year that we said, yes, black holes actually do in fact exist. And we now know it. We've seen them. Here they are. That is the event horizon. There it is, right there. You could see where there it is, nicely annotated.
Yeah, no banana for scale.
That's a big black hole.
So yeah, a little too big for a banana for scale with that right there. But it was fascinating that you looked at the simulation, the expected simulated image that came from the Event Horizon Telescope supercomputers when they did the crunching initially. And then you looked at the actual image that they got of M87 star, which we call black holes. We usually add star onto it. So like the black hole at the center of our own galaxy, because it's in the constellation Sagittarius, we call it Sagittarius A star. So the supermassive black hole at M87, because it's basically confirmed now, we call it M87 star. They looked at the simulated view and they looked at what they ended up getting with the data, and literally like perfect match. It's very rare to actually see like a perfect match happen, but bam, there it was. And that basically told us that there it is, right there for us to look at. And there was also another one I wanted to throw out here, which was a paper that just came out in the past couple of weeks, which talks a little bit about Planet 9, which I don't think is correctly named for it, but I mean that we could have a whole episode. I think we've done several episodes about what makes
what's
a
wrong with
planet.
that? What's wrong with calling it Planet 9?
Well, come on. I mean, if we're gonna, this is getting like ultra pedantic, and I don't want to get into this because it will just devolve into. I mean, I've been at conferences and I've nearly seen fistfights break out over what if Planet 9 actually is Planet 9, or if it should be Planet 10 because of Pluto and all this other stuff. And it's just like, I wish that kind of energy would be put into proposals for missions as opposed to Twitter reply wars.
Okay. Well, it is that it would actually be Planet 9, though. It would be
technically speaking
between 5 and 15.
Yes, it would. But there was, and they've been hunting for it for almost 4 years now. And of course, the observation time that you can do for it is right around this time of the year because they expect it to be pretty close to the constellation Orion. But there was a study that just came out the past couple of weeks ago that says that maybe it may not actually be a planet. Maybe it's actually a primordial black hole. Now, this study wasn't necessarily thrown out there in what I would call like 100% seriousness. It was basically sort of like, let's throw something at the wall and see what sticks. Which, I mean, honestly, that's what a lot of science is. And they basically said that this black hole would be a primordial black hole. So basically the kind of black hole that would appear in our universe very shortly after the Big Bang. So that would allow it to remain very, very small in its mass, because most of the time when we think of black holes, we think of like stellar-sized black holes, multiple times the mass of our own sun. But this one, they say, would be about 5 times the mass of the Earth. And one of the neat things in their paper is that they actually had a figure in it. And of course, if you read astrophysics papers and stuff, there's always figures and graphs and charts and other things. But
gotta have pictures.
Yeah, this kind of just blew us away because they put in a 1-to-1 scale figure of how big the event horizon for a 5 Earth mass black hole would be. And that's
there it is.
Like one of the coolest things I have ever seen in a paper before. That's my hand for scale, by the way, just to let you know. So it would be just about, I think it was 4.5 centimeters, if I recall correctly, with that there. So, by the way, if you do find a 5 Earth mass black hole, don't put your hand as close to it as mine is right there. And I just love this at the bottom. Exact scale, 1-to-1 illustration of a 5 Earth mass primordial black hole. Like, I've never seen that I've never really seen much of scale in an astrophysics paper, let alone a 1-to-1 scale with that. And that's a pretty interesting idea. And one of the people instrumental in bringing up the hypothesis of Planet 9, Mike Brown, whose Twitter handle is brilliant, Pluto Killer, with that there, he actually said on Twitter, it sure could be. So he kind of said, yeah, maybe. So
yeah, because the reason we know it's there at all is or we think that it's there, is that we're not seeing it directly. We're hypothesizing it's there because we can see the effect that whatever it is that is there has on the things around it. That's how we discovered Neptune. We discovered Neptune long before we actually saw it. We knew Neptune should be there. because of the effect that a planet the size of Neptune would have on all the other planets around it. And sure enough, as telescopes got better, we found it. We looked at it directly. And the same's kind of going on here with this Planet 9 business. There's something out there that's affecting the orbits of things that we can see that isn't consistent with the stuff that we know is there. So something must be there. But it's its gravitational field that we're actually noticing. And so it doesn't have to be a planet.
Mm-hmm.
It just has to have mass that would have the ability to warp space-time in a way that lets these things that we can see orbit the way they do. So yes, it could be a black hole about the size of 5 times the Earth that would go there. And it would be, in fact, physically quite small with a very strong gravitational well. So yeah, it could absolutely be that. And the thing about black holes is that we've, as I just said with the Event Horizon Telescope, we only just found out for sure that they exist. Black holes are black. They're hard to see. We only see them when they do things to other things, like eat stars or gobble up gas and dust. That's when we know they're there. But imagine in the middle of nowhere is this teeny tiny thing about the size of your hand floating around, just distorting space. How are you going to see that? You're not. We're never going to be able to directly see that unless it starts devouring something really close by. Then we might notice it because there'll be some kind of an explosion or energy release so as that thing gets sucked in. But yeah, they could be lurking everywhere.
Yeah.
And that's something astronomers have been thinking about for a while.
Yeah, and it's fascinating to think about that. Yeah. So, Tony, thank you so much for coming on the show. If people want to know more about you, where can they get the info at for that?
Oh, just Deep Astronomy everywhere. YouTube, Twitter, Twitch. I do it Tony's Twitch Tuesdays, T Cubed, on Twitch every Tuesday at 3 o'clock Eastern Time. I'm on Space Junk Podcast, so please check that out and download it everywhere you can get a podcast. I do that with OPT telescopes, and every week we get together and talk about space. So yeah, that's how to get a hold of me. And I want to thank you guys for letting me on. I feel like I'm sitting at the big boy table now. I'm at the big the big boy table at the cafeteria, or the popular kids group. So thank you for letting me join in today. I really appreciate it.
Well, we're glad to have you at the table. Come back to the table anytime you'd like to. So definitely,
I'd love to.
And definitely, everybody go over and check out Tony Darnell and the work that they do. It's just fantastic with everything that you do. Go throw your support behind them as much as you can, because you guys just put out top-notch stuff, and also wear amazing shirts as well with that. So it's just too good.
Thank you.
Yeah. And speaking of support, we of course can't do these shows without you here at Tomorrow. You help make these shows possible. So if you would like to help support the shows of tomorrow, what you could do, you can head on over to patreon.com/TMRO or even youtube.com/join and youtube.com/TMRO/join. You probably want to go to that one. We really like that on YouTube now, because if you get something out of this, you can literally give us as little as $1 per month to help make these shows possible. We can't do it without your support. We can't have this studio, this amazing equipment, the ability to deliver all of this to you, the ability to have myself come in and all those other people in the control room who do a fantastic job as well. This is your show, and it's amazing that you folks feel that we are worthy enough to spread this out, because this really does get to the core of our mission, which is to make everyone excited about space in whatever way that we can. So thank you so much for contributing to that and making that happen. And if there's other ways you'd like to help out, you can head on over to community.tmro.tv as well. And we've got some threads over there where you can do that. Or you can even start a thread and basically say like, hey, this is what I'd like to do for the show, and we'll definitely pull you in and help you do that. So that concludes Orbit 12.30. Until the next one, keep exploring.